the first presentation will be given by Professor Benedikt Soja from ETH Zurich, Switzerland. And your please voice.
Okay. Thank you very much for the introduction. Good morning, everybody. It's my pleasure to present our results about probabilistic neural networks for atmospheric correction modeling and then how to apply them in GNSS processing. This has been a collaboration between my team at ETH Zurich and the team at the Wrocław University of Environmental and Life Sciences, and it was guided by ESA. Now, the overview is that in precise GNSS positioning, navigation, and timing, we need accurate corrections to account for the atmosphere, more concretely the troposphere and the ionosphere. And we wanted to see how probabilistic neural networks would fare in the task. Probabilistic meaning that we not only get the delay corrections, but also their uncertainties. And then the goal was to apply that in positioning so that we can see the impact. Now, just as a wrap-up, we can see also here a map of GNSS stations on the ground, the satellites in space, and in between we want to account first of all for the troposphere and then also for the ionosphere. And in terms of variables, more concretely, we are talking about the zenith tropospheric delays or total delays, ZTDs, for the troposphere, and for the ionosphere, we have modeled both the vertical total electron content, TEC, but also the slant total electron content. Due to the limited time, I will not discuss the VTEC results here. We also computed two different kinds of models. First of all, a blind model setup where only the basic inputs like the geometry and time were given, so that can be applied very easily. And then a more enhanced model where additional inputs or features are introduced that describe the environmental conditions at a certain time. Also, due to time, I will only focus on the enhanced models. So the outline is that I will start with the troposphere, the ZTD, and then move on to the ionosphere with the STEC. So the general approach, how we create our models, is that we have a certain set of input features. Very important here is the location. So we want to allow the user to determine their corrections at any point where they want. Time is also, of course, very critical because the atmosphere changes a lot on different time scales. And since this is an enhanced model, we supplied additional meteorological data from numerical weather models like ERA5, for example, specific humidity or temperature. Now the target, so the other end of the neural network, in that case for the ZTD model is of course the ZTD, and that comes from GNSS. So these models are directly based on GNSS observations. And in terms of the methodology, as I mentioned, we're using probabilistic neural networks. There are different methodologies that one could use. For this model, we used so-called deep ensembles. So it's an ensemble approach where we have calculated a multitude of models, and then they are averaged, and we can take the standard deviation. But that would only give us the so-called epistemic uncertainty, so the model uncertainty. So we additionally apply in the loss function the so-called negative log likelihood loss, NLL loss, which also gives us the data uncertainty, the aleatoric uncertainty, so that we can get a more realistic total uncertainty. Now, for the troposphere, we have created actually a model based on only Europe, and in addition also a global model, but here for simplicity I will show only the European results. The data, so the ZTD values are taken from NGL since they have a very dense network, and you can see the stations in this map are split into different bins. First of all, we have the training stations where we train the machine learning model, then validation, which is also needed for guiding the training, and then finally we have the test stations, which are those that are used for finally evaluating the model. In addition to doing this spatial splitting, we also do a temporal splitting where we use then the year or most of the year 2024 for evaluation, since it's also then independent from the time where the model has been trained. And here we are coming now already to the performance. Here you can see the relationship between the true value, so that's the ZTD provided by NGL, and the ZTD predicted by our model on the y-axis. And of course, the closer we are at the diagonal, the better the performance of the model. And you can see that in general, the predictions fit quite well with the reference values, so they give quite a reasonable performance. Here are the more detailed results where you can see the statistics like mean absolute error as a function of each individual station. You can see, for example, that in alpine regions where it's very mountainous and a lot of height changes, it's a bit more challenging than in flatter areas. And if you look at the histogram of the mean absolute errors, you can see that on average, we are getting a performance of about 12 millimeters of mean absolute error, which is quite promising for this empirical model. Now, very interesting for this project was also to look at the uncertainties. And here we are comparing our predicted uncertainties, so the standard deviations, as an output of the neural network against the actual errors between the predicted and the modeled delays, so in terms of absolute error. So in this plot, I don't know if I can use the pointer. Not so easy. Okay. In any case, you can see here, first of all, the diagonal, which would be the perfect agreement between predicted uncertainty and real errors. But you can see that for very small errors, we still get predictions of the uncertainty which are at a minimum of something like 10 to 12 millimeters of standard deviation. So that's expected, since also for if we're lucky and there's zero error, we would actually estimate an uncertainty which is at maybe 1 centimeter, because we don't know if there's zero error. But you can see in general that also with larger errors, the uncertainty increases. So we have the maybe I get actually no pointer. Oh, thanks very much. Yeah, so as you can see here, this is the average uncertainty here versus the actual error, and it increases with larger errors and uncertainties. So that's expected, but you can see that the curve is a little bit offset compared to the main diagonal, which means that our model is actually a bit overestimating the uncertainties, so it's a bit more conservative. So of course we would like to have the perfect agreement, but it's better to be on the conservative side compared to underestimating the uncertainties, I would say. This is also evident in this plot, where you can see the cumulative distribution between the empirical, so the estimated uncertainties versus the theoretical uncertainties, where we have typically for a Gaussian distribution like 68% of the values within 1 sigma, 95% in 2 sigma, and so on. And so we can also see that we are here a little bit above with the empirical model, meaning that we are again a bit overestimating the uncertainties. Here is a breakdown of the different types of uncertainties that we consider. I mentioned the aleatoric, so the data uncertainties, and the model, the epistemic uncertainties. And you can see that the aleatoric uncertainties are mostly dominating, except for very large uncertainties where the epistemic uncertainties become more and more important. Now that was an overview of the tropospheric model. Let's switch to the ionospheric model, in particular the STEC model, which is actually quite a novelty, since previously people have used machine learning mostly for VTEC modeling, but we want to skip the step of the mapping function and directly model the STEC values based on the GNSS input. Yeah, for the machine learning model, the inputs are again the location and time, as usual. But here we also have to then, of course, describe the slant geometry, so the elevation angle and the azimuth angle, and we properly encode these with cyclic features, for example, for the azimuth, because 0° and 360° azimuth is the same. So we consider that in the machine learning model. Here we also have an enhanced model. So we use, instead of meteorological features here, features related to space weather, in particular solar indices like F10.7 or geomagnetic indices like KP index on the ground, which further enhance the model. The target is, of course, the S-tag that we determine directly from the GNSS observations of IGS stations. And here we again using a probabilistic neural network, here with the so-called Bayesian neural network. So it considers also then the uncertainties, especially if combined with the NLL loss for the total uncertainties. Again, we have stations split into the training, validation, and test sets. Here we are using less stations, only about 500, because the ionosphere is not varying that much very locally. And yeah, the data comes from the IGS network, and we ourselves determine the S-tag values that we then use in the training of the model. Here are the results. We can again see this comparison between the predicted values of our machine learning model and the true S-tag values determined from the individual GNSS stations. And we can see again here very good agreement. Of course, the larger the values, you can see we have S-tag values up to 300. Then of course the model is a bit more scattered there. We can then also analyze how the performance of the model changes with elevation angle, because as you can expect, for lower elevation angles, the performance is a bit worse, because the values of the slant tag, of course, are a bit larger, and then it's more challenging to model. So this is also nicely seen in this plot, where we can see the box plots here. So larger variations here at lower elevations, and smaller at higher elevations. And the same is true for the mean absolute error and RMSE. Now let's have a look again, not only at the predicted values, but also their uncertainties. And here we compare our predicted uncertainty from the machine learning model against the error metric, the absolute error. Again, here the box plots, and in terms of the mean value, like bind over these standard deviation ranges, we get actually these curves here. And then we can see here we have really a very good agreement between the predicted uncertainty and the actual errors. So here we don't even need to do any further calibration. So the agreement is very good already out of the box. In terms of spatial distribution of the uncertainties, we see a familiar pattern where the uncertainties are larger at the equatorial anomalies in the ionosphere. And yeah, this is also, of course, realistic, as we are typically dealing with larger values that are also more variable. Now let's do some external validation, where we want to compare our S-tag model against certain baselines. And of course, the most prominent ionospheric models are the IGS global ionospheric maps, so GIMS. There's of course a difference, because they are not giving us S-tag. So for them, we of course have then to do a mapping step, where we use the mapping function to go from VTag to S-tag. So that's the first baseline, and the second baseline is a machine learning based GIM. So it's encoding the same parameters like the IGS GIM, but just using a machine learning framework to estimate the VTag. And that we have already published in the past. So here's the example of this machine learning based GIM. We can see really that we get very high spatial resolution also, and also we compute the uncertainties. Now, the advantage here is that here we used really the same data as in our S-tag model, so it's then really directly comparable. And you can isolate the impact of directly modeling S-tag versus going to the VTag and then mapping function. However, there's one important difference, since for our STEC model, we have computed a long-term model over multiple years, so more than 10 years. And all the GYM model, they are only valid for 1 day. So they're really overfitting over 1 day, basically. So to make a fair comparison, we also had to adapt our STEC model to use additional data for a particular day to improve the performance and bring it to a fair comparison against the baselines. Here you can see the direct comparison between the STEC from the different models, from the direct STEC model, and then also from the VTEC models plus mapping. You can see that on average we have 25 to 30% improvement against the observed STEC values. And what is not shown here is that actually the best improvement is at the low elevation angles, where of course the uncertainty of the mapping function would be the largest. Now, finally, I want to highlight also the impact on GNSS positioning, where we did single frequency observations in PPP processing, so GPS L1, Galileo E1, and we only changed the ionosphere correction model. We also included the uncertainties for observation weighting and compared the results to the weekly IGS solutions as ground truth. Here you can see the performance. The direct STEC model performs by far the best, almost a factor of 50% better compared to the machine learning best VTEC model and the IGS GYM. With that, I'm at the end of my presentation. I hope that I could show you that the probabilistic neural networks performed quite well in terms of modeling ZTD and STEC values, and also give quite reasonable uncertainties, and that overall has then a positive impact in the GNSS positioning. I would like to thank you very much for your attention, ESA for funding the project, and I'll leave you with our references. Thank you very much.